would like to thank the organizers, Dan and Kavita, for the invitation, and everyone for attending. I'm sorry that I can't be with you in person. Even if I had planned to be in person, I think I would have been prevented from living where I am currently. So anyway, but it's a pleasure to give this talk, and I'm indeed going to present on some machine learning methods for computing solutions to mean field master equations in a broad sense. And I would well, make it more precise during the talk. And it will be mostly experimental, and mostly about ideas and experiments and not much theory. So there are a lot of theoretical questions to investigate if you're interested. And feel free to interrupt me during the talk if you have questions or comments. All right, so I will start with an introduction, very brief, because I guess most of you are familiar with mean field games and what I will call mean field control or optimal control of Makhine-Vlasov dynamics, MFG, MFC for short. But I would like to prepare somehow the next section by motivating or introducing controls that depend on the population. So I will call them population aware or population dependent controls. So, all right, this is a very basic view of mean field Nash equilibrium. You have one player versus population, but the population consists of many tiny players, in fact, infinitely many. And so the goal is to well, find an optimal control, alpha star, when the population distribution or is mean field flow is at mu star given. So you try to find, so here I'm maximizing a function j, but then everyone uses the same control alpha star because everyone is rational in the same way. And so you end up with mu star equal to the distribution induced by alpha star, or if it's not a static setting, then it would be the mean field flow induced by alpha star. So using more mathematical notations in a continuous time setting and continuous space, finite horizon for now, one infinitesimal player faces the following optimization problem. We can write it in the following way. So we integrate over time some running cost plus a terminal cost if we are in finite horizon. Here it's just a diffusion, but controlled by alpha. And mu hat, here is a mean field flow between time 0 and t, and it plays the role of a parameter. Somehow it is given to the player when the player tries to optimize and find the best possible control alpha. So here I'm being very vague, but what I want to stress is, well, two things. One is that there is a fixed initial distribution, typically. So there is this mu0, which serves as the initial distribution for the process x0, but mu hat, when we find the equilibrium, also starts from mu0. And the second thing is that very often we focus on feedback Markov control. So functions alpha t, instead of being a stochastic process, we can, very often we restrict our attention to controls that are functions of time and the current position of the player, x at time t. Of course, it's not the case in general, but very often we do that. We restrict our attention to such controls. And so later I will well, argue that in some cases you want to put, it's quite natural to put the distribution as well, even if it's more challenging. So, okay, but in this setting, if we write the optimal control for this infinitesimal player and we introduce the value function, then it would be also parameterized by the population distribution mu hat or the mean field flow. And we would have a value function, which would be a function for every x. This is at time 0, and it would be also a function of time if we want the value function at every time t. Okay, for mean field control, the difference is that we optimize over the whole population at the same time. So here, instead of having mu star, we have mu controlled by the same alpha. Okay, and here it's written as a maximization problem. So we try to find alpha star and the induced mu star so that we get a better total reward. If we write the optimal control problem for this setting, it would be an optimal control problem for the whole population. So we don't freeze mu hat, and mu t is directly the law of x at time t, x controlled by alpha. So we can make the same remarks as before. There is a fixed initial distribution. We can look for alpha in the form of a function of t and xt. But if we try to do dynamic programming, then naturally, well, we have to take into account the initial distribution at time t, for example, which means that while we can't really introduce a value function, which would be independent of mu, the value function will anyway depend on mu. And well, as a consequence, it would be natural to consider controls that are also functions of the population, I think. So in the case of midfield control, optimal control of Mac-Nielsen dynamics, we are quite naturally led to introduce population-dependent value functions and population-dependent controls. For midfield games, maybe it's less natural. At the beginning, we were focusing on, the forward-backward system of PDs, but then Lions introduced the master equation, which is reminiscent of having a value function of the population. Okay, so I would like to motivate, besides the fact that there is this master equation that exists, I would like to maybe motivate the fact of having population-aware controls and then discuss possible ideas for numerical approximations. Okay, here are some limitations of what I would call population-agnostic policies or population-agnostic controls. So if we take a control alpha, which as before is a function of t and x, or maybe it was noted by a, function of t and x and taking values in some action space. One first question is, how do we see the dependence on mu0? So if mu0 is fixed, then we don't care, but maybe we would like to understand the dependence on mu0, or another way to say it is we would like to understand how time can be interpreted. So here is an example. Imagine you are in a room, like your conference room, maybe a very crowded one, and you want to exit the room. What would you do? Would you take your decision only based on time and your position, or would you look at people around you? Well, probably you look at people around you. You take into account the crowd at the current time, and then you adjust your trajectory, and then you update your perception of the crowd, etc. So implicitly, when we look for controls which are functions of t and x, we are using time and using the fixed mu0 to deduce the current population distribution if it evolves in a deterministic way. It's true that we can solve the Fokker-Planck equation and we can recover the distribution at time t, but it's a very, very indirect way. So somehow the information brought by time is kind of coupled with the information brought by mu0, and it's very hard to disentangle these two. So even just for the sake of interpretability, it would be nice to have functions of the population distribution, because that's what we kind of naturally do, I think, as human beings. We don't solve the Fokker-Planck equation starting from time 0 until time t every time we want to make a move. Another possible limitation is, what if there is common noise in the evolution of the population? So this would mean that we have aggregate shocks affecting everyone, and then the population does not evolve in a deterministic way anymore. And having functions of t and x only is quite restrictive, because now if I know what time it is and if I know mu0, it's not enough to deduce mu at time t to the stochasticity. And another aspect, which is maybe closer to machine learning, is the question of generalization somehow, which is, okay, let's imagine even if maybe mu0 is fixed, but maybe the population is not going to follow exactly the Nash equilibrium trajectory. Maybe because people have some kind of bounded rationality, or so even if I solve the Nash equilibrium, even if I compute my optimal control, assuming the rest of the population is going to play in Nash equilibrium, maybe they are not going to do that. And so I would like to know how to react to potential deviations and things that I have not, I didn't have in mind at the beginning. So there are some motivations that lead us to introduce controls that depend on the population. So I will denote them by alpha tilde or pi tilde if we talk about policies, functions of x, and an element of the probability distribution on x, or some subset of this, which will be interpreted as the current mean field state. We could also add time. This would be relevant in particular if we have a finite horizon. Given some alpha tilde population dependent policy or control, we can feed it with the current state of the agent, the current population state, and we can view that as a function of t and xt, where the dependence on t is through mu t, as I was saying before. This is provided I know mu0 and provided mu evolves in a deterministic way. All right, so now the goal would be to try to learn or approximate such alpha tilde. And the idea is that we would like alpha tilde to allow us to recover a Nash equilibrium control for every possible current distribution. So we would like to be able to start from any distribution. And by using alpha tilde, we would be playing a Nash equilibrium, or we would be playing a social optimum. We would be following a social optimum. For this, in order to have some numerical methods, I believe there are three main ingredients. First, we need to decide what to do with the mean field state. Second, how to approximate the policy or the value function. So for these two, it's mostly the first A and B, it's mostly about representing these objects somehow using a finite dimensional approximation and something that we can manipulate easily in the computer. And part C is more about the algorithm, and it's about the question of learning or training these approximations so that they become close to a Nash equilibrium or a social optimum. So for mean field games, there are somehow two procedures that are needed. So there is the agent level optimization. We want the control to be optimal for the agent, but we also want the population to evolve according to this optimal control at the agent level. So this is a fixed point. And for mean field control, we just want to have the population level optimization. So in some sense, it's simpler. So I would like to go through these three ingredients step by step and propose some possible solutions. So first of all, for the mean field term, so mu, this would be for a one-time step, for example. Mu would be an element of P of X, so the space of probability measures on X in general. And we would like to have a finite dimensional representation. Okay, one easy case, somewhat easy, is if X, the space X, is a finite state space. So if you have a finite number of states in your game or your control problem, or maybe it's continuous, but you make a mesh and you do a finite state approximation, then mu can be represented as a histogram. So a histogram is like a vector, a normalized vector. Okay, so in this case, we have quite directly a finite dimensional representation. However, well, we often maybe have in mind that finite state is simpler than continuous state, but if it's finite, but the number of states is 2 to the power 1000, then it's not something for which you really want to manipulate a histogram, right? Or probably we can't even represent the full histogram in the computer. So we might want to do some approximation, even if it's finite state. And well, if it's continuous, then approximations are needed. So one possible way is to do what I would call distribution embedding. So for example, either you start from a finite state space, or you start from a continuous one that you discretize, and then you don't manipulate directly the histogram, but you try to get some kind of summary of this histogram, something more efficient. So for example, you take the histogram, pass it to a neural network that would output a short summary of this histogram, and that would be easier to manipulate. Because what do we want to do with this distribution? We want to pass it as an input to the value function or as an input to the control. So if we have a huge histogram, then it's not going to be convenient to give it as an input to another function. Another approach is to not use any discretization if we are in continuous space, and just use some parametrized approximations, for example, using kernels or using some classes of neural networks that have been designed to approximate density functions, or maybe probability measures in general. Okay, so this is for the distribution embedding type of approach. And the last one, also quite straightforward, is to just use an empirical distribution of n particles. So here we somehow come back to, so it's quite natural for the in-field game community, because we have this interpretation that the distribution should, and typically comes from n players or n agents. So we can use a simulation with n particles and use that as an approximation of the distribution. And if we have n particles in dimension d, then it's an input of size n times d. So it's finite dimensional. Okay, this is more like a list of possibilities. I'm not saying that one is better than the other, because it depends on the application, it depends on the problem. So, and it depends how we combine it with B and C later. So about part B, now let's imagine we have a finite dimensional approximation of mu. So we would like to pass this approximation to alpha tilde, or maybe to the value function. Okay, even if we do that, the function v and the function alpha tilde would still be elements of functional spaces, which are infinite dimensional in general. I mean, because mu would be an element in a continuous space. So we replace P of x, which is in general infinite dimensional, by something finite dimensional, but still mu is taking continuous values. For example, if it's a histogram, it's finite dimensional, but it is taking continuous values. So alpha tilde would be a function of some input taking continuous values. And so alpha tilde itself lives in some infinite dimensional space a priori. So how can we approximate alpha tilde and v? One simple way is to try to discretize this P of x, so that we have only a finite number of points, and we discretize x, and then we can approximate alpha tilde by a table, basically, or something which takes, so there would be a finite number of possible inputs, and so we can represent alpha tilde by the values for each of these inputs. But typically, we don't want to discretize P of x, because this is a bit too brutal, particularly if x is big, then P of x is really huge. And if we discretize it, we need a tremendous number of points in order to have a good approximation. So probably using a tabular representation for alpha tilde or for v is not going to work for many interesting examples. So in this case, we can use a function approximation. Imagine that the input of alpha tilde or the input of v is very high dimensional because of the representation of mu. Then we need some efficient function approximation for v or for alpha tilde. So here again, we can think about kernels, or in the sequel, I will show some example with neural networks. About learning, two types of, two possible meanings for learning. One is more based on, let's say, algorithmic game theory. So it's more about the procedure at the level of the population and how you update your behavior iteration after iteration, and how the population adjusts. But there is also the more machine learning interpretation, which is, well, how a machine learns how to do something based on experience, and how it uses experience to improve its performance on some task. So here we will combine both somehow, because we will use a machine learning point of view to learn controls, but we also care about the behavior of the population. Okay, I already said that for meaningful game, we have fixed point iterations, and inside we have the way we update the agent control. For meaningful control, it's directly an optimization problem. However, if we don't use these iterative procedures, but if instead we write optimality conditions, because we know the model, then optimality conditions would look very similar, because it would be a forward-backward system in both cases, or a master equation or a Bellman equation, which are both infinite dimensional. Okay, as you can guess, there are many possible combinations in terms of, well, settings. So it could be finite horizon, infinite horizon, continuous space, discrete space, etc. different solution concepts, whether it's Nash equilibrium or social optimum. And then for the three ingredients I have described, the distribution, function approximation, and the learning method, here again, there are many possible choices. So there is a huge number of combinations. And I don't want to claim that I know which combination is better. And I think it depends really on the problem and what you want to do. So instead, I will just show 4 examples of possible combinations. And just to illustrate the diversity of what is possible or some possibilities. Do you have questions so far or comments?
I think it's okay. I ask to the audience.
Okay, so I will start with 2 instances of methods, which are based on the models. We will use optimality condition, and we will look at the master equation from infield game or the Bellman equation from infield control. And then I will show 2 instances of model-free methods. But in fact, you already partially heard about it because they are related to Sarah's talk and René's talk yesterday. But I would like to insist more maybe on the numerical aspects, if time permits. So just a few words on deep learning. So maybe a 2-slide crash course on the terms I'm going to use. So let's imagine you want to minimize a function or a functional. J is a function of phi, where phi itself is a function. And this loss function or this cost has the form of an expectation, where xi is a random variable. And L is a loss inside the expectation. For example, it could be regression. So you want to match a target function, f, let's say. In this case, well, we can't optimize over all possible functions. We don't have a closed form formula, but we can optimize over some parametrized functions. And neural networks is a class of parametrized functions in which what we do is we take an input, x, we do a linear transformation, then we apply a non-linear function, psi, which is called the activation function. And then we just repeat this. So it's a composition of linear and nonlinear functions. And if we concatenate all these terms in red, the betas and the w's, these are the parameters. And I will call them theta. I concatenate everything, I call that theta. So I end up with a function phi, which if theta is given, then it's just a function of x. But I can also view it as a function of theta and try to find the best parameters to make this function as close as possible to my target function, for example. And the idea is that if I allow enough degrees of freedom, so if the width and the depth go to infinity, then hopefully I can approximate very well my target function. So the goal now is to optimize over the parameters theta. Once I fix the structure of my neural network, the goal is to optimize over theta, which is a finite dimensional object. Okay, so the goal is always to go from something which is a priori infinite dimensional to a finite dimensional representation. So theta is finite dimensional because each W is a matrix and each beta is a vector. Okay, so we would like to minimize this function as a function of theta, but there is still one problem, which is that I don't know how to compute this expectation a priori. Even if I know the distribution of xi, in general, there is no closed form expression for this, and there is no closed form expression for the gradient with respect to theta. So I cannot do directly a gradient descent. But what we can do is for a given xi, we can compute the gradient of this L tilde inside the expectation. And why can we do that? Well, because the loss function L is known, and the function phi as a function of theta is also known because it's a neural network that we design. It's potentially complex, but the computer can do automatic differentiation and compute the gradient of phi with respect to theta. So in the end, we can really compute this gradient here for a fixed sample xi. And so if we can't get the whole expectation, then maybe we can get it for a few xi, a few samples, do one step of gradient, and then pick new samples, do one step of gradient, etc. And in this way, we kind of emulate a gradient descent, but in a stochastic way. So this is called stochastic gradient descent, and this is what we are going to use in the sequel. So I hope this makes sense. I was giving the regression problem as an example, but what we are going to do is not regression because we don't, I mean, there is no clear target function. Maybe we would like to learn the optimal control, but it's not like if we were doing regression against this optimal control, we are going to find some very indirect way to approximate this optimal control. So the game will be to define the loss function so that if I find the best theta, it gives me a phi theta, a function which is close to the optimal control, for example. So I'm not saying anything about the theory, but there are many interesting questions about how to analyze the error, possible sources of error. So it could be the approximation. Is my neural network deep enough or wide enough so that it can approximate so that I can find some choice of parameters that approximates the function. This is the approximation, but then I can also ask how many samples do I need? Or I can also ask, is FGD going to converge or not? How many steps, etc. And also there are many variations. Here I'm just describing the simplest ideas, but what I have described is a feed-forward fully connected network, but there are many other architectures of neural networks. Samples, you could pick them in different ways. Optimization algorithms, SGD is a basic one, but then there are many bells and whistles that you can add to make things converge much faster or in more general situations. So that being said, the first example, so let's imagine we take a finite state infinite games with state space E, continuous time, and we look for deterministic controls. And the master equation would look like this, where calligraphic U is the solution. It's a function of T, X, and M, where M is an element of P of E. But you can identify with the simplex or a histogram with of length the number of states. So we see that it's a backward equation because there is a terminal condition, and I'm not writing the underlying mean-field games, but okay, there is a terminal condition coming from the terminal cost, backward time derivative. H is a Hamiltonian, and H star is a function defined below. But anyway, I just care about the general form here, and I want to stress that this derivative here is a classical derivative because it is a finite state mean-field game, so we don't need L derivatives here. So this is a PDE on a finite dimensional space. The input is in 0t cross E cross P of E. But potentially, if E has many states, then P of E, it would be the set of histograms with, well, of length the number of states, which could be large. So it's potentially a PDE on a high dimensional space. And so we would like to have a numerical method for this. And in the past few years, many methods have been proposed to solve PDEs on high dimensional space. So one approach is to replace U by a neural network. So this is for ingredient B, because ingredient A, we have nothing to do. We have already a finite dimensional representation of N. B, we replace U by a neural network, so the unknown solution to the PDE. And then what is the loss function? Well, the loss function is going to be the residual of the PDE. So we want this to be equal to 0. So we can basically look at the square of this quantity and try to make the square of this quantity 0 for every T, X, and M. And it sounds pretty simple, but it works, and it has been introduced by Sirignano and Spiliopoulos and called the deep Galerkin method, by analogy to the Galerkin method, but here using neural networks. So the idea in our context here is to pick a sample, which is a point in our input space. So T, X, and M. We pick a point, for example, uniformly over this input space. And then we compute the residual for a fixed theta, a fixed parameter of the neural network U theta. We compute the residual, and if it is not 0, well, then we make one gradient step in order to try to make it closer to 0. So the neural network enters at several places, and we need to compute the partial derivatives of the neural network with respect to also the input, so time or X or M. Now, how do we check whether it works or not? Well, one way to check is we don't have an analytical formula for the solution to the master equation, but what we can do is, you remember this distinction between fixing mu0 or not? What we can do is we can fix mu0, then we solve the forward-backward system using a classical method. So because it's finite state, the forward-backward system is a system of ODEs. So we solve this forward-backward system for this given mu0, and then we evaluate the neural network along the flow, and we see if it matches or not, if it matches the value functions that we compute by the ODE system. So here's an example, which is a cybersecurity example with 4 states, depending on whether the computers are infected or not, defended or not, and the action is to try to switch from defended to undefended or vice versa. So I'm skipping the exact model, but I just want to show how we can check whether the solution is correct or not. Because it's one problem with deep learning methods. In general, well, after some effort, you manage to get something that looks like it converges, but you don't know if it is a true solution or not. Maybe it's just a local minimum. You have found, a 0 for the gradient, but it doesn't mean that it is the minimum or that it is a good local minimum. So for this, it's good to have examples where we can check. So for this one, this is the evolution of the distribution. This is time, this is the proportion. And for each of the 4 states, we see the proportion evolving through time. And on the right, it is again time, but the y-axis is a value function. And I don't know if you can see well, but there are some dashed line or dotted lines which correspond to the solution obtained by the ODE system. And the bold lines are the one obtained using the neural network. And we see that they match, which means that the deep galactic method has managed to found a neural network that computes the value function, at least for this flow of distributions. And then you can do that for other flows of distributions and check that it works as well. So we don't need, in other words, we don't need anymore to solve the forward-backward system multiple times. We just solve once for all the master equation.
Mathieu, may I ask a question?
Yes, please.
This is Pierre. Yeah, so I misunderstood in the previous slide. If you take the norm is in L infinity, when you look at the residual, it's in L infinity. In what sense?
No, okay, yes, it's a good point. Thank you. So here the residual is for one fixed sample, meaning one fixed point, just one point, one t, x, and m. So at this point, we can compute the gradient, and then we do one gradient step. But because we do that, many times, it's like if we were minimizing the residual in expectation. So it would be, because there is a square here, it would be the L2 norm of the residual that we try to minimize overall.
Okay, because for this kind of equation, you expect the solution to be discontinuous in general, right? I don't know if the model you are looking at is monotone. So what's going on at points of discontinuity where this expression can be very large, right?
Yes, it's true. So, okay, I don't have the example here, but in these notes, there is an example with a discontinuity. And it seems to work well. I think maybe one reason could be that the point of discontinuity, you are never going to sample it. So you are going, with probability 1. So you are going to sample points, to the left or to the right. And on the left and on the right, you will learn, the neural network is going to learn that it should go, down and up. And the neural network is still going to be, let's say, a C infinity function, but it's going to try very hard to catch the discontinuity.
Okay, makes sense. Thank you very much.
No, sure. Yeah, I can show maybe some examples or send you later. But it's not a proof. Okay, I don't have a proof that it should always learn the discontinuity well or that it should converge. I don't have a proof that it converges to the solution to the master equation. Okay, it's just experiments. Thank you for your question. More questions or?
Not in the audience, and it doesn't seem online. So you can go on.
Another example. So let me just go back. On this one, just a summary. A was just a histogram, B was using a neural network for the solution to the master equation, and C was trying to minimize the residual by sampling points. And so, of course, we sample points, but we are not going to sample all points. So here's the generalization aspect, is that we are not going to view all possible M. We are not going to view all possible histograms during training, but we hope that for some reason, the neural network learns correct solution for all M, even if we haven't shown all M during the training. Example 2, now just to show something different, a mean field control example. And so here we are in continuous space, let's say RD, continuous time, still using deterministic controls. And we can write a Bellman equation, which would in general have the following form. So a terminal condition and then a backward equation for some operator calligraphic F that I'm not describing, but here we do have a derivative of V with respect to the measure, which is here a L derivative. So, Okay, first thing is what can we do with the distribution? Now it's a bit harder because it's an element of, let's say, P2 of RD, which is infinite dimensional. So we can't use a histogram. We could discretize, but let's try to do something different. So here I will use an empirical distribution representation, by which I mean that we take RD, we take n copies, and we replace V by asymmetric functions of the n inputs. And we replace the L derivative with a gradient with respect to X. So this is very reminiscent of the motivation of infield control or mean field gains, where we have n agents and we go to the mean field limit, but this is not the Bellman equation for the n agent problem. This is an approximation of the Bellman equation. In particular, there is, I mean, if we were writing the n agent Bellman equation, there would be some terms of maybe size 1 over n or something like this that would be around in the equation. Here we remove these terms and it gives us basically an approximation of the Bellman equation. But anyway, in spirit, it's similar in the sense that we take n points to approximate the distribution, and we take a symmetric function v to approximate the value function v function of the distribution mu. Now, because we have n, and n is typically large if we want to have a good approximation, v is a function defined on a very high dimensional space. So we need some efficient approximation. We use neural networks again, but there is some information we can exploit, which is v is a symmetric function. And there are some neural networks that are symmetric with respect to these inputs. And so in principle, it means that we need fewer parameters if we exploit the fact that we know that the function is symmetric. It's not a generic function of n inputs, it's a function that is symmetric. So in principle, we need relatively few parameters. So these neural networks have been used in particular in computer vision to recognize clouds of points in which you don't care about which point is which point, you just care about the distribution of points basically and the density of points. All right, now what about point C? Well, we could say now we have a PDE on a finite dimensional space. V is a neural network. We could use a DGM, as in the previous example, the deep Gallatin method, to solve this PDE. But let's do something different. Let's remember that this is basically a Bellman equation. So there is a natural structure which comes from dynamic programming. And so we can try to use this structure. So what we do is we use a stochastic representation for the value function. So xt would be a stochastic process, n particles, each in dimension d. This process could be just the Brownian motion, or it could have a drift, or it could even be controlled. But if it is controlled, it's more complicated because we have to feed back the effect of the neural network in the dynamics of x. But we can just consider that x is like a Brownian motion in dimension d, and then we use Ito's formula, and we get an SDE for yt, and for zt, which is a derivative of the value function, or the v, which approximates the value function. Then we discretize time, and we can use backward induction to say that, okay, if I know y, which I will express as a function of xt, if I know y at time tk plus 1, then I can try to go back and compute y at time tk. So this is a dynamic programming aspect. We go from terminal time and we go back in time. Now u represents y and calligraphic z represents z, but these are functions of potentially very large inputs. So same thing, we can approximate them by neural networks. And at each time step, we have two neural networks, one for u and one for z. And there is also one at time k plus 1, but this one is already trained because we are going to go backward in time, and we are going to do SGD at each time step and going back and going back. And once we have trained at time k plus 1, we don't need to change this neural network anymore. However, UK appears at multiple places. So it's not like if we could just update simply the left-hand side using the right-hand side, because in the right-hand side, we have UK appearing and ZK appearing, and we need to find the solution, which is really an equation that we want to solve. So what we are going to do is, again, something similar, where we are going to take some loss that is minimized when we solve this equation, basically. So here is the algorithm, which is an adaptation of the deep backward dynamic programming scheme of Lauriére and Guillen-Pham and co-authors, where the idea, it was for standard stochastic control problem at the beginning. And here, because we use this approximation with n particles, it becomes method for mean field control. But the idea is really the same as in the original paper. You go backward in time, starting from terminal time, and at each time step, you train the neural networks for U and for Z so as to minimize this loss function. And you see it's an expectation because even if you, so first of all, you want to do that for every possible starting point, xk, and the transition to xk plus 1 is stochastic. So you want to average over all possible starting points and transitions. And so we have this expectation, but we can take samples and do stochastic gradient descent on these samples. So here is a numerical example. So here again, how can we check that the solution is correct? So we run this algorithm. At the end, we get U and we get Z for every case. We have 2 neural networks for each time step. And how can we check that these neural networks are correct? Well, here again, we can solve the forward-backward system for a given initial distribution. And we can check that it matches that, for example, U, let's say, matches the value function that we get from the forward-backward system. Of course, it's very tedious, so we are not going to do that for a large number of, we don't want to do that for every possible initial distributions, but just for checking, just to check, we can do that for a few distributions. So here, this is basically a linear quadratic example with a different terminal cost, a cost which is not quadratic. So we don't have an explicit solution. Actually, in dimension 1, I think there is in the paper of Salab and Roland Malamé et al. But anyway, you can solve the forward-backward system and compare. So this is a value function in orange that you obtain for some initial distribution. And if you change the initial distribution, you get a different value function in orange here at time 0. And so the neural network U at time 0, from what we see, matches this function, except on the borders. But this is because here on this side and this side is because maybe we didn't sample enough points. So the neural network didn't get the chance to learn accurately. And we didn't sample many points because the initial distribution was concentrated around the center. Okay, so this was two instances. These were two instances of methods where we use the model because we really write the master equation or we write the Bellman equation, and then we try to solve them by minimizing residuals or by minimizing one-time increment of the equation. Now, what about model-free learning? So if, let's say, if we're in a discrete time setting and stationary problem, we can write a dynamic programming equation for the value function. What appears inside is what we call the Q function, which is if you use a policy pi or control pi and you start from X and the first action you use is A before using policy pi, then this gives us the state action value function Q. And from here, we can recover an optimal control quite easily. If the problem is known, then we can try to solve this equation, which is a fixed point equation for V or a fixed point equation for Q. But in some cases, we cannot do that or we don't want to do that, either because the model is not known. For example, maybe I don't know the reward function or I don't know the transition function. Then I cannot do such iterations, and not exactly at least. Or maybe I know them, but the model is just too complicated and I don't want to bother and trying to solve exactly the equation. So in this case, we can use model-free methods. Here is the key idea is to realize that Q star, so the optimal Q function, also satisfies a dynamic programming equation, which is this one, which is actually a fixed point equation for some Bellman operator B. And we can, if we know the model, we can try to solve it either using pointwise update or using function approximation, so replacing Q by a neural network. But this works if we have access to the model, if we are able to compute this expectation exactly, and this expectation exactly. But in general, we cannot compute these expectations exactly. So we replace that by samples. And for us, we are going to use Monte Carlo samples. So we can have as many as we want. In practice, maybe you would have a finite number of samples. So you need to be a bit careful about how you use them. But let's imagine we can do Monte Carlo samples and we have as much as we want. So for mean-free game, the situation is similar, except that we have the distribution involved. So the distribution would be involved in the transition and the reward function. But for a single agent, the problem is basically the same. The single agent wants to learn an optimal control by learning its value function, given the population distribution. Mean-field control, it is different because it is an optimal control for the whole population. So in this case, the population is really the state of the system, and we want to learn a value function, which is a function of the distribution, and also a control, which is a function of the distribution. But we can do the same thing in meaningful game. As I have said at the beginning, we can still care about the dependence on the population for the control and for the distribution, for the control and for the value function. So this is based, on the same work that Sarah presented yesterday, where what we tried to do was to approximate the value function, but as a function of the distribution. So if mu0 is not fixed, or if you have common noise or some other motivation, you want to learn the value function as a function of the distribution, and you want to learn the control as a function of the population as well. So in this case, we assume that we start from mu, the population starts from mu, you as an individual player, you start from x, and the population is going to evolve according to the Nash equilibrium. You assume that other players are perfectly rational, they are going to evolve according to the Nash equilibrium, and you would like to know what to do. You would like to know what is your best decision. But you would like to know what to do for every possible initial mu somehow. Here is again the three-step recipe. The first step is what to do with the distribution. So in this case, what we did was we started from a finite dimensional grid word distribution with more density. For example, in this picture, we have more density at the center and less density on the side. It's basically a histogram in dimension 2, but it's quite big because it's like 15 by 15. So we pass it to a convnet, convolutional neural network, which outputs kind of short summary. So this is the distribution embedding. Then this embedding, we pass it to a neural network for the Q function, which also takes X as an input. And now the goal is to train this Q function so that it represents the value function of an infinitesimal player starting at position X and facing a population starting at mu. And knowing the population, assuming the population is going to play the Nash equilibrium. And so for the training part, we used a variation of the fictitious play, so introduced by Pierre and Saïd Adikanlou in the meaningful game setting. And the twist is that we have to train for many possible initial distributions. So we add a loop over a training set of distributions. And then we try to learn control the value function, and then the control as neural networks that take as an input the distribution as well, the current distribution. Okay, I will skip the numerical results, but basically we compare with what happens for population agnostic distribution. And what happens is you can imagine that if you train a distribution, so imagine you have a policy or a control which is appropriate for a given mu0, but then mu0 changes for some reason. Well, then the control is not very good because you are still using the same strategy, but the population has changed. And so compared with that, the neural network that we trained, which has been trained to react to different populations, performs better. So it is indeed aware of the state of the population. Last few words, another example that related to what René presented, which is mean field reinforcement learning. So here we go back to mean field control. The value function is a function of the population. The policy is also a function of the population, and it is a policy for the whole population. But now this is really a Markov decision process, MDP, except that the state is a population distribution and the action space is a bit special because it is a space of feedback control somehow. But once we realize that it is a Markov decision process, we can introduce a Q function, and this Q function satisfies a Bellman equation. And then we are back to trying to solve approximately a Bellman equation using model-free reinforcement learning. And so, well, if the state space is finite, then we can use directly a histogram. The value function, we approximate it using a neural network. So this is related to the deep Q network method, or some variant of that, for example, actor critique. And to train the neural network in order to learn the optimal Q function. So this is an example in which the goal is to, we have several examples in the paper, but this is one example where the goal is to steer the population distribution from some initial distribution to another distribution. It's a kind of discrete optimal transport. And so we see that the neural network manages to learn a descent policy that starts from the green distribution towards the blue distribution, and the target one was in red. So it matches pretty well, even in the presence of common noise that affects the whole population distribution. So in this talk, it was mostly about how to learn controls that are able to generalize to distributions that are not seen, that are not fixed a priori, and that are maybe not seen during the training. So not just for a couple of distributions, but for really a large number of distributions. And the key ingredients were the distribution representation, function approximation, and how to train this function approximation. I've shown just a few combinations. So again, it's just to show the diversity, but there are other options. Even for the examples I've shown, you could come up with different combinations. The idea of combining machine learning and mean-field games, I think the main interest is that mean-field games allow us to scale in terms of number of players, and machine learning allows us to scale in terms of complexity of the game. Because using classical methods, we're quite limited in terms of complexity of the game. So state space, action space, etc., etc. So here, and common noise, etc. So here, hopefully, we can tackle more complex and more realistic examples for applications. However, we are lacking almost completely theoretical aspects. So there is a lot of work to do if you are interested. Thank you.
Thank you, Mathieu. Are there any questions in the audience?
Yes, I'd like to ask a question. Oh, good. Hi, Mathieu. Thanks for a fascinating talk. Really informative. So in the adaptive mean-field game work, which I did with Armand Kitsakali several years ago, where system parameters weren't known, we took an increasing population, but the information that any agent got was an asymptotically vanishing fraction of the growing, in principle to infinity, population, because we were concerned, because we regarded one challenge as being the actual sample size that any agent had to learn about the other agents. So in the situation here where one's trying to estimate the distribution of the population in various ways, how do you formalize the sampling of the behavior of the other agents as viewed from a single agent, or even from a control central agent?
I see. Yes, thank you. I think, yeah, it's a good point that here in all the methods I've presented, we assume that the population is perfectly well observed for the agent. And so what we feed in the neural network, well, is a perfect representation of the population up to some approximation, but there is no question of sampling, etc. Okay, if we use n agents, there is some kind of sampling, but we assume that we observe the n agents or the n samples. But hopefully this opens the door to some approximation. For example, we could say, once we have trained a neural network, for example, for the Q function, but we feed not the exact mu, but some approximation of mu, which comes from some subsampling or something, maybe it still behaves well. So this is a hope, like as an extension of what I said, but then I didn't think about how to approximate the distribution using, very few samples, which seems to be what you are referring to.
Yes.
So I'm not sure how to combine the two exactly, but.
Well, we were able to show it worked with a ergodic loss function, and so the asymptotic behavior of the entire population was asymptotically optimal with a sort of a log n, for instance, a log n sample of a population of size n, as everything was growing. So I'm sure it'll work. I just wondered if you'd studied that aspect.
Okay, no,
thanks very much.
Other questions? There was Pierre.
Mathieu, I've got another question, which is as stupid as the previous one. So on your example 2, you said that you started with the mean-field control problem, and then you go to the finite population. Okay, I don't understand the reason why you do that, because when you look at the mean-field control problem, you've got a kind of regularity of the feedback with respect to the state, which you lose a priori completely when you look at the n population game. I mean, I was wondering if you don't lose too much doing that. I don't know if I'm clear, but in the n population game, when you have two players which are very close, they could play something completely different. Okay. While in the mean-field game, in the limit problem, it's not the case, because you look at the the solution, the optimal control in feedback form. So in principle, it should be something relatively irregular in terms of space. So
I see. Okay, first of all, I think the questions are not stupid. So thank you for asking, and thank you for the second question as well. I think, okay, I don't know if it answers your question. Maybe one point is that we don't, so what I was trying to say is that we don't go back to the n player problem because I mean, this PD, the second PD is not the Bellman equation for the n agent problem. So it's, we get rid of some terms, etc. And okay, but it's true that here the value function V would be a function of everyone, but it's a symmetric function. So we kind of, so because it's symmetric, I think it's going to be very regular. So the perturbation of one input is going to be of size, 1 over n, because in fact it's symmetric.
Okay,
so,
maybe it's answers. I didn't catch the fact that it was not coming back to the n-player problem anymore.
Okay, I see. Yeah, so it's a bit different. And also Maximilien Germain and Yuan Pham and Xavier Varin, they have a proof of convergence of this type of approximation towards this continuous model. And I don't remember if, okay, I mean, I think the kind of question you ask pops up in the proof in the analysis. So maybe there is a detailed answer there, or maybe not. I don't know if maybe there is still, maybe we could still exploit what you're suggesting.
Okay, thank you very much.
There is another question.
Thanks a lot for your talk, Mathieu. Very interesting. Now, how do you envision in practice the discovery of a mean field equilibrium in a large population? I mean, whether it be traffic, you are an individual and you're trying to play the mean field game. So presumably everyone in the crowd would be doing these calculations. How do you view it? I mean,
yes,
and at the same time, if they are, this is affecting the dynamics because, they're learning something from a sample path, but then they're acting and then this changes and everybody's changing at the same time. So I'm just trying to visualize a concrete way this would go through, unless it is some top view, you're trying to learn about a system and you're just an observer and then you experiment. But so do you have anything to say about that, please? Yes.
Yes, thanks for the question. So for me, it reminds me of this first type of learning, which is sometimes particularly I have in main economics, but not only there, but people try to understand how the population is going to adapt and to learn. So I think this question is not answered by the first two methods I've presented, where we use optimality conditions, because when we use the optimality conditions, you kind of write the system at optimality, or at equilibrium, and you try to solve it. So it's really about solving an equation and not, I don't think it's about understanding how people learn. It's really about solving the equation. But the second type of methods is maybe more about learning in this first sense. Because we could imagine that the agents, try and at each iteration they improve their behavior in some sense. But however, these methods, I think what happens, if we want to interpret this as agents learning simultaneously, still typically we have a single value function and a single policy of control that we try to, in the two methods I've presented later, that we try to improve iteration after iteration. But so it would be a little bit like if we had a large number of agents trying to learn, but they all learn the same thing. So they all synchronize to have the same value function in mind. And at each iteration, they keep improving. So I don't think it really answers the question of how a large number of agents learn in parallel without, synchronizing. It's really about what if everyone in the population is learning exactly in the same way, which is a kind of reduction of what happened in reality. So it maybe answers partially to your question, but only if you assume that the agents are all learning, not only they have the same dynamics, same cost, etc., but they also learn exactly in the same way.
Yeah, they should cooperate in some sense in learning.
Somehow. So that's not very realistic. But
so that would be conceivable maybe in mean field control, not so much in mean field games. Okay,
true.
Thanks. Thanks a lot.
Yeah. So I still view this as a way of computing rather than a way of understanding how the agents learn.
Okay, so let's thank Mathieu again.
Thank you very much.